pleasure to introduce
Hey, Apollo.
Professor Liu.
Just recognized you.
He has a bunch of friends here. So it is my pleasure to introduce Professor Liu from UC Irvine. Professor Liu got his Bachelor of Science from Northwestern Polytechnic University in Shanghai, China, Master of Science from Beijing University of Aeronautics and Astronautics, and a PhD from Princeton University. He joined UCI in 1991, so he's been there for a while now. And he has a bunch of accolades. I'm not gonna list them all, but just so that you know, he's author or co-author of more than 100 journal papers, so I had lots to catch up with. And he's a fellow of the AIAA and ASME Society. So please join me in welcoming Professor Liu. Today he's going to talk about large-eddy simulation of reactive flow in rocket engine combustion chamber and turbine stages. Thank you. You have the stage.
Thank you, Professor Ba. It was a tremendous pleasure to come back here again. Thank you for the opportunity. And it's actually this morning I walked over on campus. I think your campus looks a lot more impressive than UCI because it looks more historic. The buildings and will have more characters than what we have. I think this university, your university, is very special to me because I think it was, first of all, I recognize all the Cal State universities. There are only two schools I know about, and they're the best. And one is here, the other one is Long Beach, mostly because I was associated at Aerospace, and you have the best aerospace programs in the here. Of course, the rest of it is also very good. And secondly, aside from probably UC San Diego, this is probably my first place I made this presentation. I did the seminar because I was saying that Alan Plotkin was he used to be the department chair of aero here, and he was a professor at the University of Maryland, and I was a student, and apparently he was handling or reviewing of one of my first new AWA papers. So I didn't know much about it, but I knew that he was supervising my papers, and then when I came over here, he actually moved over here too. So out of the blue called me from here and said, well, I'd like to invite you to go give a seminar here. I said, well, I thought you were in Maryland. So I'm over here now. So, anyway, but it's tremendous to be able to come back. It must be over 10 years. So now the last time I was here visiting Xiaofeng here, he was over the back. So I also am very happy to see friends over here. Pavel, actually, I was surprised. He was actually at the UC Irvine as a postdoc for a few years, and some of the stuff that he worked a bit on. And I also have a special person, Fletcher, actually, was once our program manager. We did microgravity studies, flame propagation over. I wonder how you like it being now in the university.
No, I feel safer here than in there. From Elon's group, I hope.
Anyway, so it's very special for me to be back here, and for the students over here, you have a tremendous campus and tremendous faculty. Professor Jose Castillo has been establishing this computational program, research science program. Tremendous work, and it's been very successful. I admired him for years. So, and this is my first time to do a presentation in this program, so it's very special to me. Thank you. But I'm going to talk about what I wanted to present here today. What I really wanted to present, I think about is computational science as a colloquium. So I'll be more focused on the algorithms development and the computer programs that actually apply to most of the applications that I'm familiar with, I am tasked to work on. So and I'm going to give a little more focus on reactive flow for rocket engine combustion and turbine burners, which is the concept that we proposed some years ago. And we have recently started doing some computations on that. So without saying, the introduction is very simple. Computational science, and in particular computational fluid mechanics, CFD, has and is continuing playing a major role, a significant role in scientific discovery and engineering applications. As I was reading the program description in the room that the center has, and then it was listed the computation as being one of the four discipline approaches for science. So certainly this is important, and but we're still faced with the challenge of the ever increasing demand for the accuracy of the computational methods, and as well as efficiency to solve complex problems, not only for scientific problems. Turbulence is one that can demand any kind of a computer resources, and certainly, I recently got interested in doing some simulations about black holes with the collaboration with somebody else. That could also be, DNS type of research and stability, and that's something that we're working on. I'm not presenting that, but it's certainly just shows that there is tremendous work to be done in terms of developing algorithms and connected to solving scientific and engineering problems. Engineering problems is also related to design, simulation of particularly for my case, would be flow problems. So what I'm going to list is a few engineering examples that we have tackled on, particularly my group at UCI, and say what things we have done here. So a few challenges over here for those students who are motivated in here. Of course, the CFD was very closely related to the design of airplanes. And it made tremendous impact even for our 737, starting with solving the potential flow equations, being able to predict the flow, transonic flow, the shock waves over an airplane, over winds and aircraft, was a tremendous advancement. And Boeing touts that their 787 was the first airplane that was actually used CFD in the design phase. The true CFD based on Euler and Navier-Stokes equations. Whereas the Boeing 737 was designed in the 60s. It was a very old plane, you believe it or not, but it's, and at the time it's basically mostly by Penel methods. They did at the end improve by using potential flow codes, and but they never really, from a design point of view, never really used other than boundary layer methods and Penel methods. And of course, the one that I worked quite a bit on is aeroelasticity, basically fluid structure interactions. And here was the work that we worked on many years ago using the solving the CFD Euler equations coupled with structural mechanics for, this is the model of F-16. I have to admit I did not do this computation because I was not allowed to have the F-16 geometry. But people did that with our developed algorithms, and I was allowed to show the this. Anyway, then this one is a sort of like a weekend problem. It's never funded by anybody, but we are interested in the flow of you see airplanes flying in a high angle of attack. It will generate a pair of vortices, which it enhances the lift and so on. But they have problems. They lose stability. Sometimes the one is higher than the other, that creates banking forces, which is not undesirable. And so we were developing. I worked on some theoretical work, and then later we'll say, well, let's do computation. And these are the LES type of simulations of the vortex coming off the leading edge of a delta wing. And they're all the structures associated with it. And in the end, if you have higher Reynolds, this is a low Reynolds number, because at high Reynolds number, we can't really afford to do that. It will actually break down, the vortex will break down. That is very important in terms of predicting the stability of aircraft flight, missiles too, as well as in the combustor of jet engines or so. There's a lot of vortices and fuel breakup or so. It's all related to that. So there's a fundamental science in there to understand how the vortices break up. Instability for in here is not good for airplane flight, but actually in the combustor, it's actually desirable. We want these things to be unstable, so you can break up liquid fuel droplets and so on. So the kind of understanding of this vortex stability by using computational method, is still very challenging area, which I actually had an interest, just recent interest. As I said, we're looking with some colleagues looking at the black holes, and on those also is related to the vortex stability issues. So we're using DNS and also as well as some dynamic system analysis, looking at bifurcations and so on. I'm just saying this is to motivate most of the students in computational sciences. Tremendous of work, opportunities in understanding science as well as engineering application. Although I'm giving here mostly engineering applications, partly because I needed the funding to do this work. But the black hole, I don't think I will have any funding. I will do weekend project like this, okay? But maybe this is actually the flow through a gas turbine engine. This is actually a compressor stage, fan compressor stage, where you have many, like airplanes, each blade is actually a wing, but you have many of these wings flying in the channel, and then there are rows of winds. They interact with each other, so it's much more complicated even than for this type of flow. So I moved into some of the things doing rotor stator interaction. The flow is intrinsically unsteady because the blade behind the first blade is in an unsteady environment because it's in the wake flow of the first row, and you have many of such rows. And this has a lot of aeromechanics problem. The air load will cause a lot of flutter oscillation problems of those. Even though these blades are made of steel, but they actually do vibrate. And if you excite the resonance over there, you can cause tremendous damage to all these blades. All right, a major this work was funded by Fletcher's old place and NASA. We were interested in looking at of course, supersonic jet and the noise for supersonic flight is a major issue. Supersonic flight, or even actually recently, the Navy was, well, not recently, Navy has particularly interested in this for the carrier aircraft because the crew is noise level is so high. So we were looking at noise reduction, and there's a lot of problems and challenges in terms of using computational science, being able to resolve the small eddies due to turbulence and the shear of a turbulent flow. And what you see here is the signature, the pressure signature that's been emitting noise pressure fluctuations backwards, not only just downward, because the eddies. There's a supersonic jet. The eddies actually, well, the turbulent, more structured eddies moves at a convective speed that's higher than sound, and that means that you can create what is called Mach wave emission. That's what we were working on with that. I was doing the computations. My colleague Dmitry Papamosko was doing experimental work using a tri-jet technology to reduce that. This is one of the, but before that, Fletcher actually funded us to do some microgravity studies on flame propagations. Talking about flames, here is actually now we from the flame that Fletcher was interested in the micro flames, starting on liquid pool, and for example, in a spacecraft or so. Here's actually we're looking at the rocket engine, so a big flames. Actually, we're looking at this is a hydrogen oxygen post coming out of this is a combustion chamber. This is the nozzle of the rocket. So this flow here will be supersonic, and here is from subsonic to accelerate to supersonic. And there's a fuel and air mix over here, create the flame structures. And the major thing that we're interested was that being able to understand the mechanism of instability in what pressure instability that can develop in this rocket that can actually cause high pressure, can actually cause explosions and so on. And this is actually something that Pavel actually worked on while he was with Bill Striano, my colleague. So this work actually in collaboration with that. We were doing three-dimensional Stokes DNS LDS simulations for this, and now I'll report some of the results in the end. So these are a few examples of the engine from at least in my perspective engineering applications, as well as some scientific motivations to apply computational methods to solve these problems. So my motivation, my work, since my background was more computational fluid mechanics, so we were interested in developing computational methods and computer software that can actually simulate flow problems in a wide range of engineering applications for the purpose of understanding the relevant physics, for example, the microgravity flame ignition and propagation that Fletcher was interested in from the government there. And then also being able to optimize design of the airplane or the gas turbine engines or the rocket engines there. So I've been in this for quite a while, but so in the sense that we would like to have a computational methods or computational package with different methods there that be able to handle complex geometry, because most of the examples that I showed you that I was involved in involves a lot of complex geometry. In fact, in some ways that when Fletcher funded us on the flame propagation on the liquid pool, that was the simplest geometry we dealt with, because that's the pool and we have liquid though, we have the two-phase flow, but still in terms of the geometry, it's a square, three-dimensional, it's easier. But you see from the previous slide, a lot of them are very complex geometry. So we need to have being able to handle the different geometries and line grids that can handle those geometries. And again, you can see that just from the movies over there, we have a lot of spatial and time scales that we need to resolve. There are different scales involved in here, moving and the scales for the sound too. So we need to have a code that is actually able to resolve the different spatial and temporal scales. And that's always a challenge for computational science. Being on one hand, you want to resolve the large scale of the airplane, the scales over the size of the airplane, say the Boeing 747 or so will be close to 70 meters or so. And then the cosmological scale of turbulence is very small. And similarly, time with so sound emission, then you are interested in 20 hertz to 20 kilohertz or the whole span. It's not just one narrow area, and that's easier to work with. And for so I want to basically motivate you students is saying there are tremendous opportunities because of the wide spectrum, time and space, and because of nonlinearity. Because if it's linearity, you can always separate it, study each scale separately. Because nonlinearity, the different length scales and different time scales, they all interact. If one scale affects the scale of the behaviors of physics of scales in other scales, and that's the difficulties on that. So there's a tremendous challenge in it. And then the other thing is multiple physics. For this case, we have fluids and we also have structures. We have turbulence and we have reactive flows. That at least the few that I have been interested in, or being able to have the opportunity to work on. And then we'll also be for a lot of our applications for aerospace, we should be able to handle both high-speed flows with shock waves. This is the common thing, especially nowadays we're going to hypersonics. Supersonics or hypersonics are always shock waves, and that shock waves is discontinuity in the flow field, and that presents problems of itself. And then there's a low Mach number flow that we also need to be able to handle. For example, the liquid fuel flow in the liquid supply lines and so on. And of course, we always are faced with the problem of computer time. And then we need to be able to take advantage of the modern massive parallel computers, and particularly GPUs. Earlier, Professor Barra and I and our student were talking about how we take advantage of GPUs. For engineering problems, or even for science problems, there is always a balance of accuracy and efficiency if you want to solve them, but the majority of problems. For some problems, you can say, I want to use the biggest computer to solve to do things that I haven't done before. For example, PK Young at Georgia Tech, he's going to come to visit us on Tuesday. He has done, he's going to present results of DNS results for turbulence using 24,000 cubed grid. Think about that. He's using the DOD, the Mosley computer. In the 1990s, Steve Orszag at Princeton, I was a student at the time, and he was he made a wave that he did something like a 1024 cubed, and that was the the best breakthrough in that time, right? Being able to resolve that scale. Now it's doing 23K cubes. Anyway, so these are, but then for majority of our problems, we have to be able to balance efficiency that you can solve most problems, and with the kind of accuracy you can get. And that's what we had over the years that we have to deal with. And along this, because of these constraints and desires, we have developed a code called POSSE, and that's extensively used for almost all my research, except some of the theoretical studies. POSSE actually originally was named as parallel code for aeroelasticity, evolving into a general, and that actually eventually we were doing the aeroelasticity studies more like that F-16 oscillations. And then based on that, we evolved that into a general purpose CFD code that solves the Navier-Stokes equations by finite-volume method, multiblock grid, and we can handle quite a few a few physics at least, and then including flow, heat transfer, fluid structure interaction, and combustion. And then the central part is the Navier-Stokes flow solver, and then we have the aeroelasticity solver that's actually being coupled internally, or actually through an external package too. And then we have the recently evolved into the chemical reaction solver, and they're basically the major part of this in this. And POSSE, as I mentioned, essentially, well, we haven't changed name. We should take a different name. But this one of my former students, Mani Sategi, who's now at Pratt Whitney, as being a lead aerodynamist, aerostructure mechanist, he named POSSE because, well, I didn't have a name, but he said this is actually POSSE was apparently some Roman goddess. Yeah, I'm less than. Anyway, so the major, I just give a little bit background on this. So here, there's some three-dimensional Navier-Stokes equations, or say in the Navier-Stokes that also includes an energy equation over here. And this is formulated in either a stationary frame, reference frame, or moving reference frame, where we want to deal with the rotor state interactions for gas turbine engines. So you could actually having a rotating reference frame, including Coriolis forces, so on. Any body forces where we actually have been using this to study plasma flow actuation. So we have actually electromagnetic forces that we can include in, or ion forces in there. And then we also, well, these are the, over the years, we've built all different turbulence models. Originally, when I started the code, I actually coded only the SST code turbulence model. Then we went into the SA and SSD gamma with transition models, and the LDS model, Lagrinsky, dynamics Lagrinsky, and Whale model. And we are incorporating all different technologies in DES, DDES, and so on. And that just these are the basic equations that we we were showing over here. We can treat two-dimensional, three-dimensional, axisymmetric. We have for low-speed flows, we have a preconditioner to handle low-speed flows, and we are able to do subsonic, transonic flows. And well, originally this is all based on perfect gas, but because we're working with these chemical reaction problems, where in the rocket engine we have now non-perfect gas, so we actually incorporated some non-perfect gas laws in there too. This is the basic algorithm. Is very simple. It's the finite volume scheme. So this, if you have a conservation law, and Revere was asking me why you call it conservation, this is because this is the divergence form. So this is the source term. This will be the variable that's being conserved, and then this divergence of the variable. Why do you call it the conservative form? Is that when you integrate that over a control volume like this hexahedron or here, then you will get the integral of this time rate of change of the conserved variable in this volume is related to the surface integral. In other words, whatever flux is going through the surface, and it's all conserved. If you integrate the whole domain, everything's added together, the contribution, the internal fluxes will cancel, and what you have is the source term contributing to the rate of change. And these equations are very general, not only for like fluid mechanics, but also you can formulate a lot of physical problems in terms of these, in terms of conservation laws. Now, so we'll discretize it over a grid cell, like shown over here. And then the major problem is you do discretization of the fluxes, how you represent the surface integral. And we start from the integral equation because in principle, we would like to be able to deal with shock waves. Shock waves are discontinuous. So if you really start with taking derivatives, in principle, derivative doesn't even exist. So but you can actually use integrals too, still in that case. And that's why we write it in this way. Although in practice, of course, the key is how you approximate these fluxes. How do you approximate fluxes? By using some support points, the flow where the points where the flow variables are defined, and that's the key of almost all current numerical approaches. Although I understand Professor Jose Castillo is looking at this mimetic method, which is approximates the different operators, and that's a different way of approach in this. But this is more for starting from the physical point of view, and I will come back to this in the future directions where we say we want to do higher order schemes. Higher order schemes, basically, you have to use more than one support point in order to construct the fluxes, and the construction of the fluxes is the key in terms of increasing how you can construct from the different neighbor points. The higher order you want, you will have a higher points that you need to represent, and therefore your computational cost will be high. That's why I say there's always a balance between these two. Nevertheless, with the future computer development, we are thinking about getting more points in each cell, which can be handled by GPU. GPUs will handle local computations very efficiently, and then still using the concept of the finite volume, where you can evaluate the fluxes effectively to get the key is that accurate fluxes, but also the fluxes will not result in any oscillatory behavior in the solutions due to shock waves and so on. That's called non-oscillatory solution. So in this case, in order to do the convective flux schemes, fluxes, there are various schemes that are currently more used in the community. Some of them are about our group that we do those. Some of them actually are by like a person like Vernier splitting row scheme that's been very popular. And what we have is our groups, mostly JST scheme on our own, and we have some of this is more from I don't know. Fletcher knows him. He's at NASA Glenn too. He passed away already. I forget his name. It's actually Feng Liu. You don't know him, but anyway, he passed away because of cancer. He's about my age, but anyway, we used to In any way, these are the schemes. I'm not going into details and saying this is the scheme that our group has been using, and it's basically on simply a central differencing scheme, but with some numerical dissipative schemes. But the dissipation has to be able to distinguish waves that travels in different directions. Because if you are in a flow problems, you know from characteristics that some characteristics go left, some characteristics go to the right, and that meaning that some waves will travel left. If I'm standing over here, my sound goes left and right. But if I'm moving with the fluid, then some waves faster, some waves become slower. If I move supersonic, all waves going into one direction. You cannot hear from the other side. And any numerical schemes, in order to be able to handle the convection correctly, you need to be reflecting the original physics, in other words, reflecting the wave directions. And this is just a way of distinguish the different waves. And this is particularly important when you have a shock wave, and we have a shock sensor that will sense the shock and then decide what schemes we need to use. And this is the row scheme. Phil Rowe initially started that approach, and then we have our own versions of working on that. And that's basically what I was talking about. Distinguish the waves due to contact surface, due to the upstream wave, expansion wave. There's a shock wave. This is actually a rarefaction wave, and this is expansion wave, and this is a contact surface. And in other words, we distinguish all of these in our algorithms in such a way that we can reflect the original physics and therefore be able to produce non-oscillatory solution over shock waves. And that's a major issue with the high-speed flow. And this will be significantly more severe for high order schemes. High order schemes, in terms of mathematics, if you Taylor series expansion, you could say, the truncation error is proportional to the grid size to a higher order, third order, fourth order, fifth order. On the other hand, it uses more points. And you all know, even by doing interpolation, if you interpolate a function over more points, it becomes more oscillatory. It's more likely to produce wiggles. And that's the same thing in the computational methods. And the way that you eliminate that, you have to distinguish the different wave directions, and likewise using upwinding type of schemes, and also using limiters. And this is this is the reconstruction of it's more like what I mentioned, if given a set of points, how you would interpolate that function to construct the fluxes. And the more points you use, the more accurate in terms of mathematical accuracy you have, but the more likeliness of producing oscillatory solutions. In fact, these are very relevant topics. Even nowadays, if people are doing, if you're doing machine learning, and you're using neural networks. And what neural networks are doing is more of a nonlinear type of interpolation algorithm, functional interpolation. And there, each neuron is basically represented by a lot of weight functions and an activation function. It's like providing basis for interpolation. The more neurons you use, it's like the more points I'm using in constructing my interpolation function in my numerical method. And the more layers you use, meaning that you are essentially passing more of these, stacking up more of these interpolations. And then there is the issue. If you use more neurons, more layers of neurons, more deeper learning, you're more likely to fit more data, need more data, and you need more data to do that. And you're more likely to have a better, accurate prediction. On the other hand, your solution more likely produce hallucination too, because it basically if you extrapolate using this type of a thing, you get into that situation, it gets nonsense, right? So it's actually relevant in the sense we have to balance somehow that reliability versus validity or accuracy. So this is and considering this all nonlinear problems, the limiters that I'm not going into details, but we have implemented some of the, including window, and I saw that actually on the second floor, your center has had students working on that at some third order window scheme that I saw over lunch, after lunch. So these are the few things that we worked on. We actually implemented some of them. Some of them we did not implement and we didn't think it was worth it. Some of them we did our own type of schemes, our own versions of that to tailor it to our particular applications. These research are very relevant work because I think even for modern machine learning era, there are actually many concepts are very much related. Talking about this, actually interesting enough, we just had our program review on Tuesday from the Navy. We're doing one of these turbine-burner research. And then before that, we had also an Air Force project, and the Air Force program manager was a different one, but not our program. But he passed by our problem. You probably know Chiping Lee, and he was basically saying that he went into a conference, not conferences, his group, his contractors meeting, and mathematicians, physicists, and also engineers all together. And then they were talking about using data simulation, essentially, the new type of machine learning type of methods for studying rocket combustion problems. And then the mathematicians talking one language, and then the physicists then a little bit different. But then he was saying that in the end, that mathematicians always say, well, we actually have this mathematical trick to do this and that. And then they will also find out that what he was saying is that they're saying, it seems to me a lot of these mathematical tricks that worked have some physical background, actually can be traced back to there is some physics that has to be reflected that you obeyed and therefore it worked. That's interesting. It's coming back. I was thinking that a lot of these schemes, when we do these numerical schemes that we develop over the years, we also have the same issue that we really have to think about the original flow problems, where what are you trying to resolve? What are the physical propagation, wave propagation or diffusion mechanisms? Okay, I think I'm taking too much time. Now we have developed our own. I saw actually downstairs a student do a presentation on using third order Runge-Kutta scheme. We have our own developed new Runge-Kutta scheme that is able to handle efficiently. We actually usually use a 4-stage or 5-stage scheme that we tailor our coefficients based on stability analysis, and by splitting, we have a way of splitting the diffusion and convection. Our non-Stokes equation basically a diffusion reaction, and later when we do a chemical reaction, we also have to this is actually doing time. We have a way of doing time accurate using the pseudo-time method. I'm going to skip on that. But major thing here is this recently this is actually ALGS, is still time steady. But we actually formulated an implicit LU SGS method, which actually can be effectively applied on parallel machines, and also taking advantage of we have a splitting algorithm to handle the stiffness due to chemical reaction. If you have a chemical reaction, the time scales can be widely spread. It can be you have some reactions very short, some reactions very long, and probably is very familiar with those things. So in order to do the numerical method, our numerical scheme time step limit is always limited by the shortest time scale or the fastest chemical reaction in this case. So we have to somehow handle them separately. We attack this problem in several ways. One is mathematically in the numerical method, so that we will be relieved by the stability limit. But on the other hand, you can only do so much on that. And also, as I was saying, if you do not respect the original physics, if the original physics is dominated by a very short time scale and you're not resolving it, you're not going to expect you have a good answers, right? So somehow you have to deal with these short time scales. Another way to deal with that is say, let's go look at the original physics. Is it any way that we can relieve that problem by representing those short time scales by some other average time scales? Just like in turbulence, like I don't want to resolve with the smallest turbulent eddies, but is it possible to represent some the effect of those smallest eddies by some mean flow quantities or larger scale quantities? And that's something that we're working on. And Pavel actually worked on that with this on this flamelet modeling. That's sort of like in concept. Did you work on flamelet on that time too?
I worked with Bill on flamelet modeling implementation, and I also worked with Steve Pope back in.
Steve Pope was the one that
back in Cornell.
Yeah. The PDF type of. So we are still. I mean, that's more. I'm not presenting anything on that part. But that's what I'm saying, that we are attacking the problem, the physical problem, in various ways from the computational side and from the physical side. And Professor Strignano was the one who was actually developing these flamelet models that will handle the stiffness problem with the chemical. And Pavel made actually quite some contributions over there, I remember. Now here's a way of what we also have, as I said, we have to handle multiple complex geometry as well as moving reference frames. In a gas turbine engine, the rotor and stators are moving relative to each other. So the grids can never be really big, unless you have can represent everything together as like unsteady, accounting for the blade motion. Otherwise, it's very difficult. So what we do is say we do one stage. One reference frame is attached to the rotor, one reference frame is attached to the stator. But in between, we have to somehow pass information, and this is what we call a sliding mesh algorithm. So we have various ways of passing the information between the different rotor blades, but reflecting the original physics. For example, these passing information methods not only are needed for the physical boundaries, but also in terms of we're doing parallel computing, we have to do pass the information between different CPUs. So there's a lot of implementation as well as theory related with that, because we need to be able to conserve energy, conserve mass and momentum, and of course, in reality, this type of thing is very sensitive to what variables you choose, whether you actually, what's the effect of in terms of the entropy if you conserve momentum only or no energy or so. So we have quite a few studies on that, and we have different options for doing this. Now, I'm not going to go into details. Let me just, I have 10 minutes more or so. So let me give you some of the examples we did. And this is one is, I'm just showing how we treated multiple blade rolls by doing sliding meshes and the interpolation method that can preserve the original physical quantities, physical conservation laws. Oh, okay. I want to, of course, we have to deal with the MPI and about the parallel compute, massive parallel computing. Most of our computations are done on the one I'm going to show. Most of them are done on the DOE machines. It's nice they have a big machines, but the problem with those is you have to wait in the queue for too long a time. And of course, we're on the lowest priority because our work is more of what they call release A, which is basically no restriction, but you still need to go through the security clearance thing. But we are on the lower priority in terms of the computers. But we do have all the different parallel algorithms we can use. I mentioned that we actually, in order to treat the chemical reaction terms, we have developed our own splitting methods that will be able to take into account those chemistry and turbulence modeling that related to the source terms. The stiffness all comes from the source term. Chemical reaction, this is actually a species transport equation. Y sub I is the species mass fraction, and there's a source term which is basically reflecting the reaction rate for each species. And then there's the transport properties and all these coupled to the energy equation at the chemistry over there too. Turbulence model has turbulence production equations there. And those are taking into account in our time margin splitting algorithms, which we have one that we can not only allow us to march in time efficiently, but also being able to, if I do reach a steady state, it will preserve a steady state. In other words, it doesn't depend on the time margin algorithm. All right, I think the finite rate model, I'm not going to talk too much about that. We're usually using a very simple model. Yeah, that's our splitting scheme, too much details in there. I'd be happy to discuss this with anyone, but the aerodynamic side, I'm going to skip that. Let me just show you a few examples where we did these the challenges of each problem. This one is Onera M6 wing. It's a transonic flow case. In other words, it's just the airplane. The wing comes in, and we generate a multi-block grid. And this is actually, at the time when we're doing this, is sort of like being able to do a completed wing is quite complicated. But nowadays, we just do it. Anybody give me a geometry, you'll be able to do that. So here, what is shown is a pressure distribution. And what is important is that you can see this is the green is low pressure. And all of a sudden it becomes, the blue is low pressure. And all of a sudden there's a line over here, it becomes higher pressure, which is essentially where the shock wave is. And the shock wave gets stronger even near the tip region. Shock waves gives the right vibration, also gives it pressure loss, and therefore drag for airplanes. And that's a major problem for this is called transonic flows. In other words, the flight Mach number is actually less than 1.0. Our 787 flies about, 737 is a cruising Mach number is about 0.7. The original 737 is 0.76 or so. Now it's a bit higher, but then the 787 can fly at 0.86, Mach number 0.86. On the wing, the Mach number is actually beyond 1. It's supersonic flow, and you can see a shock wave. And in fact, you can on a nice day, if you fly across the Atlantic or the Pacific, and if the weather's right, you can see the shock standing on the wing. That the sun shines on the right way, and then the air is just damp enough that you can see the refraction of the light is just like a shadow graph, a photograph, and you can see the wave standing on that. And those are I saw only once when I was traveling from Atlanta to Switzerland, to Zurich. The one I still remember the Air Swiss Air. Swiss Air does not exist anymore, I think.
How is that?
It's back? Okay, but I think it disappeared for some time, didn't it?
Under Lufthansa.
Okay, under Lufthansa now. But I used to like them. But anyway, that's I saw once. And that's being able to predict these shock waves is the key. The shock waves are reflected over here. The pressure, this is the low pressure, meaning high speed, supersonic flow, and all of a sudden terminates with a shock wave. And that's the one that this shock can trigger separation of boundary layer separation, causing vibration of the wing, as well as loss of increase of drag. So being able to capture these shock waves is the key in terms of doing airplane design, and that's where we have made these contributions in being able to predict the shock waves accurately. And we have, this is an open case for comparison. Now, those are steady state. In a way, it's easier. Well, nowadays we say, well, as long as you have a good turbulence model, it will work fine. They make the harder one is actually looking at the flow. For example, this is the model. It's actually just a very simple flow. It's a flow across a circular cylinder. And that's everybody actually in fluid mechanics study that. As for invisible flow, it's actually just a potential flow, and you can estimate flow is symmetric backwards and forwards. But in viscous flow, it never be like that. And then the first year fluid mechanics course tells you how do you predict the drag over a circular cylinder, the pressure drags and all, separation also. But it's in the problem that's still no real definitive answer, because for different Reynolds numbers, it moves differently. Being able to predict the separated area, and this is the turbulence being developed. Why are we interested in that? Because this helps us to understand separation, helps understand turbulence development, and it's actually a model for landing gear noise. When you're at a low speed, when you landing gear is pretty much like a circular cylinder, so the flow coming in, you actually feel next time you fly. I mean, you get to land. I was once flying from Beijing to Hong Kong, and it was midnight, about 2 o'clock, because I got delayed a lot because of typhoon also. But then at 2 o'clock, the pilot said, "We're going to land." And then I hear the pop of a pop, and that's basically the deployed landing gear. And you feel that actually the vibration and the noise, because these vortices are developing on the landing gear. But that's okay. That's normal. You do that. But all of a sudden, I heard a roaring of the engine, and I said, "Well, that's not good." Means he couldn't land. He had to pull up. He had to, really. And then he didn't say anything. But after a while, he pulled up, and he said, "No, unfortunately, we couldn't land because there was too much gust." So, people actually, most of them were asleep, anyway, but I was actually worried. Because the next day I had to give a seminar there, and it's already 2 o'clock in the morning. I didn't get, in the end we got there, after we circled around about half an hour and eventually landed. And I got to the hotel about 4 o'clock in the morning, and my talk was, I think it was 11 o'clock in the morning. I still was able to do it. Okay, so this is the type of things we can do. And this one is a supersonic jet. And this is the one that we are very much interested in, the performance of the jet. Anybody have looked at the rocket launching? You can see that behind the rocket, there's this diamond structure. They call it jet diamond structure over there. And that, of course, has a lot of effect on noise, a lot of effect on the signature of an airplane, okay, IR signature or other signatures. So we of course, that also relates to the performance of that. So this is what we're simulating type of things we are doing. This is a large-eddy simulation, being able to resolve, these are the shock wave intersecting with each other, being reflected from the free stream. The jet is coming from the engine, and then the outside air, we are simulating a flight condition. So the flow from the outside of the airplane is a shear layer there, and then there's a shock wave coming from the supersonic jet that hits the shear layer, being reflected, and then interact with the bottom one, and these are actually traveling, and you can see this diamond shape. But there's this shear layer that's creating a lot of turbulence eddies, and those are most of the shock waves and these shear layers create sound waves. And this is the detailed, more what we call Piltdown criterion colored vorticity thing. So you can see all the different structures. What we do is we take these eddies. These eddies send pressure perturbations, which is basically sound, noise radiation. But these radiation, if you just use our Navier-Stokes equation to propagate them out, you get that garbage after a while, because all our numerical method has dissipation, some level of dissipation. sound waves are so tiny, and then if your numerical schemes are not, unless you use tremendous resources, there's going to be some numerical dissipation, and you will not be able to resolve the far field sound. So what we have to do is we develop a Green's method based on Fox-William equations. Then you can actually take this signature from the near field and then propagate the sound signal to the far field. Look at the sound signature and being able to. So we will likely be able to modify the nozzle and being able to reduce the noise levels. And here's the one that NASA funded us on this project. Just after you, there was a different division on the noise one. Wait a second, what happened? So here is yeah, so you can see the noise signature propagating, and we have two different coaxial jet or axisymmetric jet, and we're able to show that we can reach by doing the new design, we're able to reduce the sound level by 12 dB in some areas, and that's significant. 12 dB. In dBs is magnitudes of really sound pressure level. It's very difficult to do, and we have numerical simulations coupled with. I think so here I'm going to go quick. This is actually the turbine-burner concept that we are simulating the flow through a turbine rotor. This is the turbine. It's a 1.5 stage turbine, means we have 3 rows of blades. And I'm going to go through all this just to show you. This is the with transition simulations. The rocket one, I really try to have the rocket. This is the rocket one. This is Pavel work. At least touched on this. This is what we are doing the simulations of a. There are 42 injectors coming off upstream, and then they igniting, burn, and then they go downstream. What we are interested in, these are the injecting ports. So we actually simulate the grid all the ports inside the long posts, and then there's also the combustion chamber, main combustion chamber. And what is important is that we'll need to resolve the pressure signals. The instability will develop in the chamber. The combustion enhances the pressure perturbations, and if they go in phase, then you can end up having the pressure grow and then cause damage to the Pavel is familiar with the problem. And now we use actually after our 3-dimensional simulation, we use DMD to decompose DMD to identify the different modes that exist, the instability modes in the chamber. Okay, I'm going to go, and that's the turbine burner concept is, I can give a separate topic on that in the aero department, where we propose burning, not combustion. Usually it's in the combustor, but we are proposing to burn not only in the combustor, but actually continuing in the turbine itself. Usually people worry about high temperature, but in the turbine, you realize you're taking out more work. So if you burn by taking out more work, you can maintain a constant pressure. And by doing that, you will actually approach more of the Carnot cycle, constant temperature burning. I can actually get more thermal efficiency and therefore higher thrust levels. I'm not going to go through this. This is the recent Navy project that they funded us on exploring actually injecting fuel in. This is the injecting ports, injecting fuel in the turbine stage, and we're looking at how it will react, looking into potential redesign of the turbine blades to absorb this heat without exceeding temperature to provide more power. Okay, I'm just going to summarize. I'm going to skip the summarizing what we did and what our code is capable of. Instead, I'm just going to point out a few directions what I'm interested in, and I hope some of the students here in the joint PhD program or masters would be motivated to go into PhD. Would be interested in working on. And here's what I think is we have done a lot of numerical method for the applications of what I think next time we would need to do to develop high order schemes. But the high order schemes have to preserve the merits of what our current finite volume schemes. And this will include being able to handle complex geometry, be able to provide non-oscillatory solution of shock waves. And we have to have high order accuracy, but without excess increase in computational time and storage. And that means we really have to think about how you take advantage of the GPU structure. And we have to also develop an effective method to treat stiffness due to chemical reaction. And of course, there are the physical side. You have to have better turbulence closure models, reaction models, real gas effects, and whether we use machine learning to do that, use machine learning to develop these turbulence model, closure models, reaction models. I think those are good areas we can go. And two-phase flow, and this is my, I personally have interest on that because of, as we're working with the Navy, they were very much interested in these detonation engines where you have shock waves and they want to use liquid fuel. Navy doesn't want to use hydrogen. Okay, we're talking about hydrogen technology. When I talked to them, they said, "Well, forget about it. If you want to do hydrogen, don't work with us. We don't want hydrogen on board." Liquid fuel, the liquid fuel detonation engines where you have a lot of high detonation engines basically have detonation waves, shock waves that will interact with fuel, with liquid fuel. So that would be a tremendous area that I think in computational science that we can make contributions. Well, I overran a bit.
That's perfect. Are there any quick questions?
Be happy to answer the questions.
So,
Yes,
what kind of reaction models do you have implemented currently? You mentioned Bill's work on flavor.
Well, we have the methane. It's a simple one-step reaction that we had before. That's the easy one. But we also have the hydrogen oxygen. But high ones group had a simplified model on that.
Right. So are you integrating the reaction in time explicitly according to our needs? Okay. Yeah.
But the flamelet model that we're developing, we're actually trying to develop a JP5, which is what the Navy is interested in. They're just wanted a JP5.
Yeah, I mean that's the beauty of a flamelet model, that you have your mixture fraction progress variable and something else.
Yes.
And the fuel can be arbitrarily complicated.
Yes. But you just build a table separately.
Yeah.
Yeah. So we're still working on that. For now, the flamelet model works on our we have a new student who implemented the flame model in my code. Okay, we moved away. When you were there, one of the students was using OpenFOAM to do things. So we moved away. When I joined this, everything is using my code because we have a multi-block structured code, which is much more efficient, and also we're able to do things on ourselves. So we moved into that. The flamelet model right now. Sylvain, who's from Spain, who's been working with us on that, and he had a paper in the AWH conference in January on that side, but he withdrew it. He said his code didn't work reliably, so we were going to work. He's trying to put it in the summer. Let's see.
I have a quick question.
Yeah.
When you have limiters,
yes,
and you have your RK4 scheme, do you apply it at each stage?
Yes, we do. We do. The stage for the convective part, we do evaluate at every stage. For the diffusion part, we actually evaluate it not at every stage.
At the end of the step.
We actually depending on how many stages you're using, 5-stage scheming, we're in the odd stages, and then in the other one we do differently. And we use multi-grid, and then in the multi-grid we don't evaluate them on the course group. With very pertinent question that the nitty-gritty is in the inside.
Any other questions? Yes.
One quick question,
Yeah,
just to get your confirmation, because you are authority, the MD, we have a lot of students over here. Do you use the Euler equation for your code? Euler is the equation of without considering the physics term. But how can you make sure that your simulation still conforms with the physics? So what is the key point over here?
No, we say Euler. Well, not really solve. Almost all the results we're showing were not solving just Euler equation. We're solving the Navier-Stokes equation, which does have viscous effect, diffusion, and everything in there in reaction. The only Euler equation result was that F16. That's because we're interested in the flutter situation. In the terms of flutter, it's mostly the pressure force on the plane that actually is exciting the structural vibration. In that case, we're using actually the Euler equation, and we worked with them. What happened was that the Air Force had a program in Florida called the Seek Eagle, which is essentially doing flutter simulations for their fighter planes. What they have to do is every time they change what they call a store, which means a weapon, missile. Every time they change one of those, they need to rerun simulations to map out a flight envelope where the pilots are told not to fly in, or somewhere you can fly in, somewhere you cannot fly in. If you're flying outside the boundary, you can have vibration, you can have a flutter problem, and then you can actually crash the plane. So, but that depends on the store a lot. So they have to run those very quickly. And in the past, they relied on this NASA code from NASA Langley based on potential flow. And I worked on that a little bit. And then I was actually in the summer visiting NASA Langley, and I saw John Edwards. John Edwards was in their aero elasticity group. And I said, well, why don't we work on, moving to an Euler? I have a way of treating all the moving boundary conditions quickly. Because then he said, well, why don't you come over and spend the summer with us? So I went there for spend the summer, and they gave me a quick grant afterwards. I said, okay, so this is what you do. So once we got the Euler code, the Air Force actually got interested, and they actually funded me and a small area elasticity company, where they developed this code, and now it's called ZOS. And that code is based on Euler, and they have used that for, Seek Eagle now is sort of using that. And then after that, I don't know anything about it, because this is all out of me. And they hire 2 of my students, and that's it.
Well, let's take, another question, yes.
Okay, very quick point. So you there's one slide that shows you solve the acoustic wave field differently at the turbulence field, right?
For the rocket.
Yeah. Was that solving the Helmholtz equation?
No, it's it's not Helmholtz equation. It's basically based on the Large-Eddy simulation, time simulation of the whole chamber with reaction and everything.
I mean, away from
what is actually using dynamic mode decomposition. So you have the time sequence, okay, your numerical simulation time sequence over the whole chamber, and then you do the dynamic mode decomposition, which will identify the frequencies, the most energetic frequencies, and the most shapes. And they may, if you have a original Helmholtz resonator, if you do DMD, it will automatically show you what you will reveal that. But of course, in our case, it's not a pure Helmholtz resonator problem. It's a has reaction, it has everything in there, and therefore, whatever the mode is identified is different from theirs. So we actually compare with experimental data to say whether it's the first mode tangential translation lateral, or let's say longitudinal and transverse modes. So we were trying to identify with DMD. DMD analysis of our CFD simulation data, but it's purely Navier-Stokes Large-Eddy simulation data set. And it's also coupled with the difficulties actually, the injection of the post fuel is quite long. And what they have done, they've shown is that these instabilities are very closely related to how long these posts are. You have to resolve those. And that's actually, at first I didn't quite believe in those, but in the end, actually, it does actually have some truth in it.
Okay, let's thank Professor Liu again.
Thank you very much. Thank you for your attention. Oh, I should, that showed the last slide. I should acknowledge the people who did this together with me. I should have shown this. So a lot of work with my postdoc, Yalu Zhu and Jung Tao. I think you met Jung Tao at the time, but he's not at NASA. He's now at NASA Ames, and he's well, for a time he was able to still live in Irvine and working in NASA Ames, but I don't know about now. I haven't seen him lately. Yeah. And then Professor Bill Srignano, who was for the rocket engine, basically, and Dmitry Papamovsky, who was an experimentalist on the jet noise, and that's where we got the NASA support with him. So these are the major contributors, along with a lot of other students or so. But the major co-development part along the way, there are many students, but the Juntao and Yalu were the ones who were able to. You know, working in a university environment with each student to contribute something, it's very difficult to maintain the code because once they leave, you don't know where it is. And it's not like a company can continue on that. I have pieces of code scattered all over. So these two were able to actually somehow integrate them, and I try to maintain some sort of a consistency. It's a part of a university. Anyway, thank you.